and it's question 13. And we left off yesterday in doing a damped oscillation, and we were saying, look, this is basically, it looks like a normal sine function, but if we go there, boom, 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 it goes up, and then it's a little bit lower, and it's a little bit lower again, and it's a little bit lower, and then it basically dissipates to nothing. And the one question that they've given you on this is number 13. And here is the formula. It's K e to the negative ct. The cosine of that w is actually omega t, right? And they told you that K was 4, which is good. And they tell you that C is 1.6, which is good. So the only guy we need to get is this omega thing, which is basically, in our world, I call that B, right? So that would be BT. And they give you the frequency, which is 3. And we know that frequency, if we go over here, is B over 2 pi. And if you rearrange that, then B can be 2 pi f. So now I know B, and what I call B, they call omega. So that's where that guy comes from. So omega is 2 pi, the frequency, 2 pi 3, and that is 6 pi. So y is K e to the negative ct, the cosine of omega t. And we are being asked to essentially fill in the missing values. So instead of K, I'll put 4. Instead of C, I'll put 1.6. And instead of omega, I'll do 6 pi. So there is your answer to question A. And in part B, they ask you to graph it. And it's going to look like that, but all of the pictures, well, not all of them, 2 of the pictures look like that, and the other 2 look like that, in which case don't pick them. But the easiest thing, isn't it, is just to put that into Desmos and look at the picture. And you pick the right picture, and you're finished. So that is one and only one example of what a damped oscillation formula would look like. And the one that they want, I believe, looks like this. And in my case, it was the first picture. Right. Any questions about that one question? Is there anything you're not sure about? Are we good to move on then to the next chapter? We're done. Chapter 5 is over. And we're now going to
I may have missed the first half of the problem.
Okay, here we go. So they told you this is the formula for a damped oscillation. In the question, they tell you K is 4 and C is 1.6, which is really useful because they put a 4 there and a 1.6 there. And they also told you what F is equal to. And that isn't the number that I need to use. I need to find out what this guy called omega is. And I was saying that guy I call B. So I go over here and I say, okay, frequency is B over 2 pi, check. If you rearrange that formula, B is 2 pi F, and omega is what they call my B. So omega is 2 pi F. So omega is 2 pi 3, 6 pi. And the omega is that guy there. So that's where the 6 pi goes from. The 1.6 comes from the C, and the K comes from the 4. And these 2, and indirectly that one, are given to you. That help?
Yes, I think so.
Okay, that was just a very quick version of what I just said a moment ago. So let's move on.
And then I did have one more question
Sure.
regarding yesterday's.
Yes, I like to hear
You
questions.
may have said it, and I may have missed it. I've been down with a cold for the past week, so it's relatively hard to retain stuff. But I'm doing better now. So I was wondering, how can you find the difference between a sine and a cosine wave? What's
When
the
you mean, how do you
difference?
find the difference in whether
Yeah.
the formula should be a cosine or a sine, that kind of thing?
Exactly.
Right.
Yes.
So they will use something like this. If you see a sentence that says the displacement is 0 when t is equal to 0. So if you see a phrase, something like that, right? Then what that means is that you're starting here. And that means that it's a sine function.
Oh, okay.
And if they say something like the maximum displacement is when t equals 0, well, they're talking about the highest starts at 0. And so they're talking about a shape that looks like that. And so that means a cosine.
Okay. And then if there's like a multiple choice graph, like four pictures of the graph.
Go into Desmos, take your answer and look at their 4 pictures and see which one looks like yours.
Yes, but will a sine always start at 0, 0, and then the cosine will start at the maximum number?
In the questions you're going to see, yes. The only time that's not true is if you had a thing like 3 plus 2 sine stuff. Right?
Yeah.
In that case, it would start at 3 before it did what it did.
Yeah.
And if it was a cosine, it would still start high, but it would start, like up here somewhere. And it would still look like a cosine. You see it starts there and, it starts at the bottom and this one kind of starts at the top of it. So I can tell that's a cosine and that's a sine just by looking at where they begin. Can you imagine a little invisible dotted line?
Yeah.
You see how that one starts on the dotted line and this one starts above it.
All right, that helped clear a bit of it up. Thank you.
That was a good question. Glad you asked. Any other questions? Right.
I do not have any currently, no.
No, nobody else either. Cool. We are now moving on to a totally new chapter. Chapter 6. We're going to begin with 6.1. We are going to be looking essentially at circles, and in particular things called arc length and area of sectors. And it's a little bit different. A lot of people find it a little bit easier, which is good. So let me show you. Oh, I am so pleased. That actually looks like a circle because most of my circles look like X. That is a circle, right? And if you take a circle and it has a radius, it's the distance from the center to the outside. And this is me just reminding you some things that you hopefully should know. The circumference of a circle can be given as pi times the diameter d. You can also do the circumference of a circle as 2 pi r. Are you all comfortable with that? Those two formulas for circumference of a circle. So if you walked around the outside of this circle, the distance c would be 2 pi radius. Now, if you want to do the area of an entire circle, there's typically only just one formula. Well, that's what you would be doing if the question involved a complete, right, a full circle. But sometimes that's not what you get to deal with. Let's imagine that I had a circle, and I'll just bring that. And I go from here, but I don't do the whole circle. I'm only interested in this bit from here to here, right? And I'll from A to B, right? So we're dealing with a part of a circle, right? And I would like to know the length that if you were a little fly and you walked along from here to here, what would be your distance, right? And that distance is called an arc length. So that's how we describe it. So I would say the arc length AB in this case. And we typically use the letter S. I guess that's because in physics, S means distance. And the formula for calculating it is very simple. You might think, oh God, that's going to be quite hard. It's not a whole circle. If it was a whole circle, it would be, you know, this guy or this guy. This is only a bit of a circle. Well, I just need to tell you one extra piece of information. If I tell you the angle in the center here is theta, then the formula for the arc length is just r times theta. Isn't that a nice, simple formula? The radius times the angle theta. Now, there is a little thing here that's very important. If you want to use this formula, you must make sure that theta is in radians, right? That's important. So here's an example. Suppose, oh, there's my little r for radius. Suppose I have a circle whose radius is 10 centimeters and the angle at the center is 2/3 pi. And I want to find the arc length. Then the arc length S is r times theta, and that's 10 times 2/3 pi. And we want exact answers here. So that means you leave your answer like that, right? You don't go and find out it's, you know, 21.3456, right? We don't want that. We just want you to get the answer and call it good, right? So if the radius was √7, wouldn't you just go √7 times 2/3 pi, and that would be your answer, right? The only time you will turn that into a decimal by using your calculator is if the question says to 2 decimal places. That would be the only time I would ever think about changing it. Now that's a pretty straightforward question. If you tell me the radius and you tell me the angle in radians, I can tell you the length of that arc. But what happens if I tell you in the second example, and I tell you the radius is 5 meters and the angle is 30 degrees? And I still want to know the arc length. So it's going to be S equals R theta. And that's going to be 5 times something. But that something is not 30 degrees. So the answer is not 150 meters, which if you think about it is an awful lot of distance, isn't it? A radius of 5 and you're going to go 150. It just sounds wrong. Doesn't that mean then we need to convert degrees into radians? Okay, so here we go. So the degrees into radians formula looks something like this. The radians will equal. Anybody want to tell me what the formula might look like? How do you turn question?
180 divided by that number.
I didn't catch the beginning.
It would be like you would treat pi as 180 and then the bottom number would just be 180 divided by 30.
Oh, you're definitely in the right place. You divide by 180 and it's pi. So the formula for getting degrees and turning them into radians is degrees divided by 180 pi, right? That's the formula, right? So you do divide by 180 in pi. I'll do the answer to this and I'll try and prove to you why that's the formula, right? Just to show you where it comes from. So in this case, the radians is going to be 30 over 160 pi, which simplifies down to 1/6 pi. Now, I got my little guy handy. I'm trying to find my unit circle here. There we go. Can you see 30 degrees is 1/6 pi? You see it works. In fact, if the angle happens to be on the unit circle, couldn't you just use the unit circle and say, okay, 45 degrees is going to be that guy, and 300 degrees is going to be that guy. But you can imagine they might then, and they will, put in 17 degrees or 22 degrees, right? Things that are not in the unit circle, which it means that we do need the formula, right? So I now know what the angle that I need to use. That is the real value of theta. So up here is going to be 1/6 pi, and I get the answer that the arc length would be 5/6 pi, which is about 3 and a bit, roughly.
Would you want to like label the units for that, like meters?
You should really, shouldn't you?
Okay.
So if it's centimeters, call it centimeters. Yeah, you should. I think you're okay in Desmos, because doesn't Desmos kind of put the unit there for you, so you don't need to remember it. And in Desmos, you would type in obviously 5/6 pi, not Desmos, WebAssign, I mean. Okay, let's try and prove to you that this formula works. Okay, so 180 degrees is pi. Agreed? That's kind of what you were saying earlier, Cassandra, right? 180 degrees is pi. So won't 1 degree be pi over 180? Would that make sense? Divided by 180, right? 1 degree is that. So if I wanted to know what degrees is, wouldn't I just multiply this answer right, this fraction, by the number of degrees you want? Does that make sense? So if you want to convert from degrees into radians, which technically is probably the only direction that you're interested in these questions, then this is your guide to go to. So far, so good. So let me see if I can find some examples. Oops. Okay, that's weird. Right, I'll just make up my own. There's something wrong with the homework. Well, it's not that there's something wrong with it, it's missing these questions. So evidently for some reason, I picked the wrong one. So imagine you want to find the arc length and the radius is 2 inches and theta is pi. Then r times theta, 2 times pi, 2 pi. Would you agree that question is pretty easy to do? Well, let's take a horrible one. I want an arc length and the radius is the square root of 7. And theta is 35 degrees. So this is like the exact opposite, right? A horrible version of that. So S is going to be R times theta. It's going to be root 7 times, can't use you, right? 35 degrees is not what we need. We need to find out what that is in terms of radians. And the answer is degrees over 180 with pi at the end. So 35 over 180 pi. If you have a fraction and you want to simplify it, and the numbers are a little bit on the big side, you can go to your
Go to
calculator.
736.
Sounds about right. You go 35 divided by 180, and then you hit the math button, choice 1, and you turn it into what you just said, 736 pi. So 736 pi. Not really much you can do with the answer. But that would be the answer, and I guess we'll put inches again. So that would be the answer in inches. If they said, give me the answer to say 3 decimal places, so I might pretend the question said that, give me the answer to 3 decimal places, we would simply just go 7 times square root of 7 times pi, and then divide it by 36. And to 2 decimal places, it would be 1.62, because you would round up. So if they don't mention anything, they want that answer. If they say to 2 decimal places, they want that answer. So far, so good. There's not really that much I can do except to make a puzzle out of it. So imagine that you've got a circle and you don't know what the radius is. But the angle here is pi upon 3. And the arc length, which is this guy, happens to be 3 pi. So I know the arc length, I know the angle. What I don't know, and what I'm going to try and find, is the radius. So how do we tackle that question? You start with your basic arc length formula, right? And you put in 3 pi, you put in r, and you put in pi upon 3. Haven't I essentially got a little equation with an unknown value r? And as long as you do it to both sides, it's okay rule. Great. Right? As long as you do it to both sides, it's okay rule. So what do I do to both sides to find r?
Divide by pi over 3.
Okay, so you take that guy and you divide them. I'm going to call pi upon 3 a third pi, right? Just because it looks nicer. If you can, shouldn't you cancel out the pi's right away so that they don't clutter up your working? And what I've really got here is 3 divided by a third, which I happen to know the answer is a 9th, but let's show you on the calculator. Top number 3 divided by, remember, put a bracket around it, 1/3, answer is 9. So as long as I tell you any 2 of the 3, can't you find the other one? So if I tell you r and theta, you're just going to multiply them. But if I tell you s and theta, right, you can solve it this way. So there is one more permutation, right, which looks something like this. So this angle is 200 degrees. And the radius is 10. So I'm telling you theta is 200 degrees. I'm telling you the radius is 10. Oops, that question is too easy. But I guess I'll do it now since I've started it. You're being asked to find S. S is R times theta. S is definitely 10, but isn't that not the angle that we need? That's the angle in radians. So if I convert that guy into radians, won't it be 200 over 180 pi? Which, if you go down here, you go 200 divided by 180, and then do a little fraction thing on it, it ends up being 10/9 pi. So in this case, the answer is 100/9 pi. That's not the one I wanted. I was trying to find one where the angle was missing. So this is my last one. Suppose we have a guy that looks something like this. And the distance S is 50 centimeters. And the angle in the center is say 3/4 pi in radians. We're being asked to find R. So S is R theta. S is 50. I don't know R, but theta is 3/4 pi. So what do I do to both sides to find R?
Divide both by 50. Wait, no. You have to move the.
Now that one is not going to come out pretty. I'll leave the pi in the bottom and I'll just do the 50 divided by 3/4. That way I can get an exact answer. And hopefully that'll turn into a fraction we can deal with. And the answer is 200 over 3, so you get that. So far, so good. So if I give you any two out of the three, can you figure out who the third one is? Using this as your starting formula and then just solve it. So let's do an application of that. Need kind of help here because I'm not a bike person, a bicycle person. If you are, what's the radius of a normal bicycle? Anybody got a vague number that's kind of close to it? Any ideas what a bicycle radius might be?
32 inches.
32 inches. Really precise. Okay. And you can tell I'm not an artist. That's a bicycle. I'd probably take it back to the shop if it looked like that, but that's a bicycle, right? And in this story, right, the person is pedaling and one revolution of the wheel. Do you know you can have these little clickers every time it does a revolution, it clicks, right? So it keeps track of your revolutions. He finds out that he can do 10 revolutions per minute. Nah, 100 revolutions per minute. Right, he's pedaling fast now, right? We want to know what his speed is in the units, miles per hour. So I know the radius of the wheel is 32 inches. I know that it does 100 revolutions per minute, and somehow that is going to become a miles per hour. Now, I don't know if bicycles have this. I know cars have them. Don't you have a speedometer and a thing that tells you your speed? And you know, the way they figure out what your speed is they essentially have a way of counting revolutions of the engine, which means revolutions of the wheel, right? And so they can do a quick calculation and it goes to the machine. So we're doing a primitive version of that. So first thing I'm going to do is I'm going to find out what the circumference of a single turn would be. In other words, how far would you travel in just one revolution? And so that is simply 32 times theta. If you do a complete revolution, isn't that just 2 pi? And so that is going to become 64 pi. Now, if you do 100 revolutions, then you're going to get a distance, so I'll call it distance now. And it's going to be 100 times that guy, agreed? Right. One revolution of the wheel, that's how far you would travel in 100 revolutions, right? And the units right now are in inches. So I've tried to keep things exact as long as I can, but I'm now going to go 100 times 64 times pi. And let's say they said up here that they want the answer to 1 decimal place, right? So that ends up being 20,106.2 inches in a minute. Ooh, I wonder how fast this guy's going. Do you know if this number is really big? Can we pretend that he's cycling down a really steep hill, right? In which case you could go ridiculous high speeds, right? Well, that is the distance that you travel in 1 minute. But we want to know the answer in miles per hour, not in inches per minute, right? Which is what we've got here essentially. What do I need to do to this number to find out how far you would travel in an hour? That's how far you travel in a minute. What do you do to this number to find out how far you would travel in 1 hour?
Divide it by 60.
Divide or multiply?
Multiply.
Yeah. I mean, if you do that in a minute, isn't 60 minutes an hour? Aren't you going to do 60 times as much, right? An increase. So 60 times that answer. And that's going to be inches per hour. Now, don't be too put off by how big this number is. 60 times 2106.2 comes out, at least in my calculation, at 120,6372. But that's inches. Inches
So
per hour.
divide by 12 to get feet, and then divide that by 5,280 to get miles.
Oh, she nailed it in one. Did you catch that, guys? Divide it by 12 to get feet, and then divide it by that 5,000 number. So I will do that.
Wait, it is that, right? 5,280? I'm trying to remember.
5,280. So I'm going to take this number and divide it by 12. Won't that give me how many feet per hour? Right, I'm traveling. So 1,206,372 divided by 12, and we get still a big number, but not as bad as it was. 100,531 feet in an hour, right? And 5,000 and how many feet in a mile?
That's 280.
5,000, say again?
5,280.
Which is, I believe what you said, Katie, wasn't it?
Yeah, trying to remember back to 6th grade.
Oh God, yeah, I totally agree with you. If you take this guy and divide it, right? So this guy here, and you now divide it by 5,280, you have got, oh, what a nice number. Essentially 19.0 miles per hour, which is actually a pretty realistic number. Can you imagine someone could cycle at 19 miles an hour? I was just worried that maybe the numbers I started off with were a bit weird. But are you comfortable about all the kind of number crunching that you have to do here to just come up with how fast something is going in miles per hour? And there are various questions which I'm going to make sure are on your homework that look like that. There's one I remember to do with a bicycle, just like this one. And there's another one to do with, do you know those steamboats, paddle boats that you have in the Mississippi River? Do you know the ones with the big, big wheels? When they want to know how fast they are going, at least in relation to what the boat's doing, not what the current's doing, don't they just figure out the distance of one circumference and how many of those revolutions they do in a minute? And that becomes a speed. So you get a question not unlike the one we just did. You can also have, I don't know if this one is one I'm thinking of that's in WebAssign, but there's one, if you orbit the Earth, isn't the Earth just a big circle? So you could have a question like, at what speed are you going if you orbit the Earth every 3 hours, right? And you could do a calculation like that. And now that I've thought of that calculation, you orbit the Earth in 3 hours. What's your speed, right? Now, if I wanted to actually calculate that, if you imagine this is the Earth and you're orbiting the Earth, basically isn't one orbit the circumference of the Earth? So I am going to go and look online, and I'm going
actually, they'd have to orbit it quite a bit further away from.
Right, I'd add 100 miles, so I'm not crashing into mountains as I do it. Agreed. So I'm going to put in Earth radius. You can't see me doing this, but I'm doing it. And did you know that the Earth's radius is 3,958.8 miles? And so I'm going to make the radius 4,000 miles for the reason you just give, because I don't want to crash into buildings, right? I want to be flying above the Earth. So I'm making the distance that we're doing. So you can imagine the Earth's inside it, right? And I'm flying a little bit above it. So it's 4,000 miles. Now, I wanted to know what's the speed. Well, don't I just need to find out what the circumference, right, is, and then divide it by 3. Great. So I need to find out what the distance I would travel, right, in 3 hours going around the Earth. So that's the radius. Then if you went round the Earth once, it would be 4,000 times 2 pi. Would you agree? If you go round the entire circle, isn't theta 2 pi? And that comes out, well, I won't even bother what that comes out to. I'll just write in the answer here. That's 8,000 pi divided by 3. And we're pretty much done. And let's say that the answer needs to be to the nearest whole number. You are traveling really fast if you can orbit the Earth in 3 hours. But aren't satellites and all sorts of cool stuff up in space, don't they travel at really fast speeds? And the reason they can get away with it is that there is, well, it's really, do you know if you go really fast in the air, isn't one of the problems you get is air resistance? And isn't the other problem is that you heat up? If you go really fast, you get really hot really quick. Now, if you're up in space, would you agree there is no air resistance worth talking about? And as long as you don't smash into anything, haven't you basically got no resistance of any kind that's even going to cause heat? And so you can go 20,000 miles an hour. I wouldn't want to do it, but I bet you could do it, right? If you went up and then you
Space
put on the
shuttle
rockets.
orbited at like 17,000 miles an hour.
Right, so it's a totally doable number. And so I'm happy with that one. Are we good with arc length then? A little application, tell me S or tell me R or tell me theta. The only thing you really need to be careful of is make sure that the angle is always in radians. Okay, sometimes they sneak a 40-degree on you. Well, that's a lot. Right, next fella. Area of sector. Well, I don't want to do that today. I want to start that fresh tomorrow. So I want us to go back and look at this formula here. Remember the one to get radians? It was degrees over 180, and then you did a pi. Remember that guy? Suppose I want to change my answer into degrees. So somebody says the angle's pi upon 7, right? Or the angle's 7/11 pi, you know, something like that. How do I turn that into degrees? Because they may well ask you in some questions to tell me the missing angle, but they want to know it in degrees. So we have to figure out how to take this guy and use them with that one.
Just move over the 180, so multiply by 180 and then divide by pi.
You see what she said there?
Mhm.
Okay, so take an example. Suppose I tell you that the angle is pi upon 18, right? You won't find that guy in your unit circle. I mean, if it's in the unit circle, couldn't you just cheat and look at the unit circle, right? Get the answer easy. But suppose it was pi 18. Now, if you want to know what that is in degrees, it's 180 times pi over 18 divided by pi. And these cancel out, and basically you've got 180 times an 18th, and the answer you get is 10 degrees. You comfortable with that calculation? So you may get an answer in radians, and if the question wants the answer in radians, then great, leave it. But if they say, no, I want it in degrees, or I might want it in degrees to 2 decimal places, then you need to be able to use our new formula, which is this one, instead of that one. Now, Katie, did you memorize that, or did you figure it out? You want to explain to people?
I just solved for
Again?
degrees.
Hmm?
Oh, I said I just solved for degrees. So I just,
Uh-huh. Oh, so you just did
Multiplied.
essentially some algebra.
yeah.
Okay, so for those who want to see a proof of this formula, I'll try and show you what she did. We're going to solve an equation for degrees. So as long as you do it to both sides, it's okay. So if I multiply both sides by 180, I get that, right? And then if I divide both sides by pi, do you see we got the formula that she found? It's quite a good technique in math that if you know one formula, that you can rearrange that formula to find other things. And the go-to technique is, as long as you do it to both sides, it's okay rule, right? So you multiply both sides by something, you divide both sides by something, what else? Add, subtract both sides, or square root. That's the typical operations. And combinations of those will allow you to take this on, well, essentially any formula and create a new, hopefully useful one from it.